Good morning. It's John Gilkison, Mr. Aero Stealth here. It's Monday, January 10th, 2022, and I thought this morning I'd do try to do a quick video on the Mercedes-Benz EQXX prototype long-range low-drag energy efficient car, which I've been seeing quite a few videos on YouTube over the last week or two, and it seems to me many of the presenters have been getting the main facts about the EQXX wrong, and this is the reason I wanted to shoot a video. One of the best YouTube videos out there I've seen on it was the original fully charged video. Fully Charged is a show out of England, and you should watch it, although they may even have a few of the facts wrong. For example, they're saying has a 100 kilowatt hour battery pack, and I've seen other sources that says it has a 107 kilowatt hour battery pack. But these are just small details. Mercedes-Benz is claiming 620 miles of range, and I'm not real clear on at what speed they're claiming that range. It's never said, and that's an important thing to know. But I think I have some clarification on that issue also. So anyway, so one of the first things I did, just for your edification, was just download an article. So just to be clear, here's what we're talking about. We're talking about this car right here. And they're claiming that it has a drag coefficient of, I believe, 1.173. And for example, the fully charged show said 0.18, which I believe they have wrong. Article says it has just some quick facts on it. It has 201 horsepower. It has a top speed. It's limited to 87 miles per hour for efficiency's sake. They're claiming 620 miles of range, or 1,000 kilometers, which is kind of a benchmark figure. 107.8 kilowatt hour battery pack. 0 to 60 2 miles per hour in 7 seconds, and I don't understand in what universe is that too slow. No one has any real need for faster 0 to 60 times. It's the difference between a want and a need, and they use a flat plate rather than liquid cooling. Now the fully charged show showed that they did have air inlets in the front, but they didn't make clear on what these air inlets were for and what they did, but they are for cooling, and they're louvered off most of the time. Now here's the major point about the EQXX. If you're going to move away from liquid cooling, this air flowing over this plate cools the battery, but this only works with the aerodynamics. And the reason I'm saying this is if it had the coefficient of drag of, let's say, a Chevrolet Bolt, it would be drawing so much power at highway speed that it would need liquid cooling. But they're claiming down to, I think, up to 6 miles per kilowatt hour. So, and that's well below 200 watt hours per mile. This kind of energy consumption just doesn't require as much cooling. So that's my major point here. If the car wasn't aerodynamic, the air cooling wouldn't work. It wouldn't work well enough. But the aerodynamics is what makes it possible. And this is what I hope to demonstrate right here. So, first place, I'll just show you a road load diagram. I have a road load diagram. This is for a 0.179 drag coefficient, and I don't have one for a 0.173, but as you can imagine, it's close. It's within a few percentile. Now right here, side by side, I'm going to show you a 0.23. So in my left hand over here is basically a Tesla Model 3 or Tesla Model S. And as you can see, how I've made the bottom lines match up, that the slope of the line is less and its peak power needs at top end isn't as high. The blue part where my hand is rolling resistance, and it's pretty much the same in both cases. And so this is what you're looking at. And from this graph you can pull numbers. And I'm going to do that real quick, but I want to show you this chart first. And this is a very important chart. This is just a chart of how lowering the aerodynamic drag of a vehicle improves the efficiency. And it has, at the bottom it has speed, okay, and on this side it has the drag coefficient, and the flat line at the bottom is 0.312, which would be a legacy car maker's offering, like my Chevrolet Bolt. And up at the top, interestingly enough, we have a 0.172 drag coefficient. And if you count down 1, 2, 3, right here, 0.232. So this line here would represent a Tesla Model 3 or an S, and up at the top, the very top line, this one would represent the EQXX. And let me give you some quick numbers here. At 100 miles per hour, it's 41% more efficient than a standard car, and a Tesla, for example, would be 23% more efficient. So it's about 18% more efficient than a Tesla at highway speeds. Now that's at 100 miles per hour, but here are your 50 to 70 mile per hour regimes right here. Okay, and I do have some stats I pulled off of there. At 55 miles per hour, you'd be able to squeeze 574 miles of range out of the car. Now when I did the original math, I was calculating on a 100 kilowatt hour battery pack. A 7% improvement to a 107 kilowatt hour battery pack would get you up just over about 614 miles, I believe. And that's just by the numbers. So I don't know what else is going on here with the car. But what many of the presenters get wrong online is the fact they think that they can get this range out of improvements in the battery pack or efficiency improvements in the motors and so forth. And yes, there is a little bit to be had there, but the main story here, the large majority of the improvement in range is reducing the road load of the vehicle by lowering the coefficient of drag. And that's what they seem to be missing. They'll even talk about the aerodynamics like they know something about it, and then they'll move on and try to attribute all the efficiency gains to other things other than the aerodynamics. And I don't know why they do that. And this is the reason I wanted to shoot this video. But what I'm seeing at 75 miles per hour, for example, is only 433 miles of range. Let's say 450. So I think Mercedes-Benz is probably quoting a range figure for something in the neighborhood of one of the test regimes they use in Europe is at 57 miles per hour. And I think that's what they're quoting. I'm just guessing. That's a wild ass guess. It's a WAG. So anyway, what we have here And this is all compared to a Tesla. But at 60 miles per hour, you have, let me see, at 55 miles per hour, a Tesla is 16% better than a legacy car, which is 0.312. But the Mercedes-Benz is 29%. You have a 13% gain over a Tesla right there, just by lowering the drag and reducing the road load. At 75 miles per hour, and this spread gets even bigger the faster you go. At 75 miles per hour, a Tesla is 21% more efficient than a legacy car, but our Mercedes is 36%. And that is a 15 degree spread, percentage-wise, right there. So, well, there you have it. I would like to see more aerodynamics put into electric cars. This is the secret to improving their range. See, as long as you're driving a gas car, my truck, for example, has a 36-gallon gas tank. Every gallon of fuel is equivalent to 10 sticks of dynamite. So I'm carrying around 360 sticks of dynamite and energy in my truck when I have a full tank. And so this is why aerodynamics is not of critical importance to gas cars, because you have so much energy density in the fuel on board, you can afford to waste it. But with an electric car, a 100 kilowatt hour battery pack's only equivalent to 3 gallons. Whatever range you get, you're getting on 3 gallons equivalent of fuel, of gasoline. So this is why aerodynamics is of critical importance to electric cars. And they need to have lower drags. If Tesla wants to go from 320, 350 mile range cars up to cars in the range of 400, they really need to lower the drag coefficient. They need to lower it from 0.23 down to the 0.18, 0.17 range. This would be half a CD point. 0.05 CD lowering would get them there. One of the other things you get is you can get a car that'll do 100 miles per hour and get 100 miles per gallon equivalent while it's doing it. And what you need to do is go below 0.18 to get there. That's what does it. And I'm just totally amazed at the number of commenters out there who just don't understand this fundamental fact. Road load is road load. The blue is rolling resistance, and this reads out in kilowatts over here, okay? So at 100 miles per hour, the rolling resistance here maxes out at about 10 kilowatts. But at 100 miles per hour, this 0.179 is requiring almost 33 kilowatts of energy total to propel that vehicle down the road. And the only way to reduce that is to reduce the drag, because this figure right here is the majority of your road load. You know, you can get low rolling resistance tires to lower this some, but on electric cars they generally haven't. So that's my message. So this is Aero Stealth signing out here. And, happy electron guzzling, everybody. Watch out for those electron monoxide fumes when you're running your car in your closed garage. So take care. See you on down the road, everybody. Bye-bye.